Hey there, Calc 2 crew, and welcome back to the Daily Problem Set. And today we're going to be taking a look at section 11.5. We're talking about alternating series. Remember, should have already taken a look at the lecture content for the video. We're just going to take a look at some extra problems to sort of reinforce what we're talking about. Now, in alternating series, you have a series that alternates its sign between terms. So we're still adding things up, but if we think about the numbers on the list that we're adding, we could start positive and then get a negative number, then a positive number, then a negative number, then a positive number, a negative number, or it could, be vice versa. So with an alternating series, we would say if the alternating series, the sum from n equals 1 to infinity of negative 1 to the power of n minus 1 times b sub n, which if I expand this out, we have b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6 plus so on and so forth, where b sub n for all those terms are greater than 0 because the sign is, right in front. Satisfies, if this satisfies the following two properties. First, that b sub n plus 1 is less than or equal to b sub n. This means the terms must be decreasing in magnitude. So they have to be getting smaller in magnitude if we ignore the alternating sign. And secondly, we need that the limit as n goes to infinity of b sub n is equal to 0. If these two things are true, then the alternating series that we have is convergent. So what's nice about the alternating series test is it's great for alternating series and it's relatively quick. We do want to make sure that these two conditions are met, and the type of alternating doesn't matter. It could start positive and then be negative like this shows here, or it could start negative and then be positive. Really makes no difference there. Let's take a look at this first example. Test the series for convergence or divergence. We have the sum from n equals 1 to infinity of negative 1 to the power of n minus 1, all divided by ln of n plus 3. Now I want to make sure that the terms are decreasing in magnitude, and to find this b sub n, what b sub n is, we want to sort of look past or temporarily exclude the alternating sign. So when I look at this series that I have here, I say, well, okay, so then b sub n, if I just want to talk about what b sub n is, it's just 1 over ln of n plus 3. It's just that log term in the denominator. And if I want to check to see that this is decreasing, and this is actually a nice example, we could probably show it with just some inequalities and talking about how the log function behaves. But if I want to show it in what I think is a very nice way, I would say work with the first derivative. So what I would do is I would model this after a function of continuous variable x. So I would look at the function 1 over natural log of x plus 3. And I would even maybe choose to rewrite this. You can use quotient rule. There's no harm in that. But I would maybe say, well, let's make this ln of x plus 3 to the power of minus 1. And we would differentiate this. We would say, well, what is f prime of x? Here I'm using chain rule then. So derivative of stuff to the minus 1 is minus 1 stuff to the power of minus 2. And I can rewrite the inner function back inside. And then times the derivative of the inner function, the derivative of natural log of x plus 3. And technically that's more chain rule. That would be 1 over x plus 3. But then the derivative of x plus 3 is just 1. So this is where it would stop. And if I clean up this derivative, I could write this as negative 1 all divided by, in the denominator, I have x plus 3. But then I also have this ln of x plus 3 to the power of minus 2, and I can bring that down in the denominator as well, and write that as ln of x plus 3 squared. So this is what we get for our derivative. What I want you to notice is that f prime of x is negative. So we'd say, well, since f prime of x is negative, this means that f of x is decreasing. And important to point out that when we're talking about this, because the log function is a bit tricky to say that it's, not going to alter the sign, luckily in the derivative we see we're squaring it. So it's always going to be something that's, positive. But I also want to take time to mention that the interval we're considering it on, when we write it into this continuous variable, would be from 1 to infinity. And when I think about natural log of, 1 plus 3 or ln of 4, and things that get larger than that, I shouldn't have any sort of concerns about which part of the log function I'm working with, right? So I'm away from where it crosses the x-axis. I'm away from where it's down in quadrant 4, for example. So we got a nice part of it to work with. But so this is great. So this is a great way to show it. Like I said, you could make some critique on this with, inequalities and get there as well. We can use this as strong justification that b sub n plus 1 is going to be less than, I think it's less than or equal to b sub n. We know it's going to be less than if we take a look at any specific two consecutive terms. But, when we talk about these things getting, very, very, very small, we like to sort of include sort of that less strict equality. So this is the first condition that we wanted to check, or condition 1. Bam. The second thing I have to check, and there's just two things I have to check, would be now taking a look at the limit as n goes to infinity of b sub n. So you say, well, now I want to look at the limit as n goes to infinity of 1 over ln of n plus 3. And there's not really too much to say here. We could sort of talk about it colloquially, but I want to make sure I have good notation when I write this out. And in that regard, there's really nothing to kind of write other than the result. But we would say, well, the log function grows without bound. So some argument along the lines of, infinity plus 3, I mean, really no such thing, but that's still infinite. And natural log of something headed to infinity is also unbounded, that's infinite as well. And placement is everything here. It's in the denominator. So we have 1 over something headed to infinity, which is going to go to 0. So this limit is 0. And for that second condition, that's what we wanted to show, right? That the limit as n goes to infinity of 1 over ln of n plus 3, or this is my b sub n, goes to 0. Since these two conditions are met, we could say then our original sum, which is the sum from n equals 1 to infinity of, it was negative 1 to the n minus 1 power over ln of n plus 3, is convergent by the alternating series test. And I like to abbreviate this so I'm not writing it out all the time, but you do want to make mention of the test that you're using. You do want to give sort of a shout out there. So alternating series test. Let's take a look at another example. I want to test the series that I have for convergence or divergence, and here's actually given out longhand, which means I want to try to find some closed form for it. So we could go ahead and we could actually, we could start by just trying to find b sub n. I think that'd be a bit easier, and then we can fix the alternating sign with it. So I'd go here and I would say, well, what's my first term? B sub 1, for example, would be 6 over 7. B sub 2 would be 6 over 9. B sub 3 would be 6 over 11. And we can really start to see the pattern. So maybe I want to work with a few of these values, but maybe I don't need everything on the list to sort of see what's happening. But what I want to do, and this is very similar to what we talked about back in 11.1, back with sequences, is I want to try to find a closed form for this. So I want to try to find some pattern, and I want to try to call on the index here, this little sort of subscript that I have, in order to make that relationship. So I'd say right away, notice all of these have a 6 on top, so I can just pop a 6 in the numerator. No one's going to have any complaint about that. What else can I say about the denominators? They're all odd numbers. And they just move by consecutive odd numbers, but they don't start at the beginning. They start at 7. And if we remember back to how we say we define those odd numbers in sort of a discrete math sense, we would say, well, that's 2k plus 1 for odd numbers. I remember we said for the even numbers that would be just 2k, but here I'm focusing on odd numbers. Although this isn't going to start right at the beginning of the odd integers. So here, and I'm going to use n instead. That's our standard notation. So we'll say 2n, but, well, here I got to be careful because I want to reference that subscript. So for the particular value, and I'll write this in a closed form later on, for the particular value, I'd say, well, this is going to be 2 times 1. I'm going to let n be 1. But then plus, what should I add to this, right? So 2 plus has to be 5 to bring me to 7. And then I can see if this is going to help me out with any of these other ones. So next I want to try to reference this subscript 2. I'd say, well, this is maybe 2 times 2, and then should be also plus 5, right? 4 plus 5 gives me 9. And hopefully this will continue to sort of follow suit for the next one, right? I'm thinking 2 times 3 now, and then plus 5. And sure enough, 6 plus 5 brings me to 11. And so on and so forth. So this allows me to sort of reference those subscripts. So, okay, b sub 1 is 6 over 2 times 1 plus 5. B sub 2 is 6 over 2 times 2 plus 5. B sub 3 is 6 over 2 times 3 plus 5. So in general, B sub n is 6 over 2 times n plus 5. I got sort of that little stray sort of glitch, so I'll fix it because you're worth it. If you're watching this video, you're worth it. And that's what I have for B sub n. Now, if I want to actually write the series out, and I can, I think it's not bad practice, though to be honest, I really just need to notice that it's alternating and then find B sub n in order to use the alternating series test. But just so we're sort of getting a complete survey of what's going on here, let's say the sum from n equals 1 to infinity, since I'm starting at 1 and then going through, and I have this part of my generating term, the big part of it, the part I want to work with, 6 over 2n plus 5, but now I just want to fix this alternating sign. So we start with -1 as a base, and it's going to be to some power on n, but always the difficult part, I think, when we're first doing this is trying to get that just so, because the first term should be positive, the second term should be negative. Since the first term should be positive, I don't want it to be -1 to the n. This is bad, because when n is 1, I get -1 to the first, which is -1, which is negative. So that means I have to shift it just over by 1. And you could either do n plus 1, or in this case I would do n minus 1, so that when n is 1, I get -1 to the 1 minus 1, or that's -1 to the 0, which is positive 1, making that first term positive. And then for the second term, when n is 2, I get -1 to the 2 minus 1, or that's -1 to the first, which is negative. For the third term, when n is 3, I get -1 to the 3 minus 1, or that's -1 to the power of 2, and -1 squared is positive 1. So everything's working great here. Definitely, you know, when you're fixing that alternating sign, I think it helps to sort of talk through it a bit, maybe check a couple of the, the first few terms, make sure that it's working the way you're intending it to. But we got it. But now I have my alternating series written out in this nice closed form with my capital sigma notation, and I want to use the alternating series test. So again, we already said this, so we don't really have new information, but we know now that B sub n is 6 over 2n plus 5. And I want to know, is this decreasing? And I think looking at it, it's fair to sort of see that it is. As n gets bigger, the denominator gets bigger, so the fraction gets smaller. But I really like working with derivatives. I think, no one's going to not be impressed with that. So I would model this after a function of continuous variable x, 6 over 2x plus 5, and that's, on the interval from 1 to infinity. And then I would differentiate this. And, no harm in using quotient rule. So, okay, I'm going to rewrite the old denominator up on top, times the derivative of the numerator, which is 0, and then minus. Now I'm going to rewrite the numerator times the derivative of the denominator. Derivative of 2x plus 5 is 2. And then all over the old denominator squared. And here this first piece, 2x plus 5 times 0 is just 0, so that drops out. And I'm left with -12 divided by 2x plus 5 quantity squared, which is definitely negative, right? So we'd say f prime of x is negative, which means that f of x is decreasing, which means then that my b sub n is decreasing as well. So b sub n plus 1 is less than or equal to b sub n, which is that first condition I want to check. Make sure the terms are decreasing in magnitude, and I can use a derivative to help out with that. From there's only one more condition to check. Alternating series tests can be a bit quicker than some of the other ones we've seen. I want to take a look at the limit as n goes to infinity of b sub n. And we built b sub n ourselves. That was the 6 over 2n plus 5. And as n goes to infinity, well, here we can sort of talk about it. The denominator is going to go to infinity, and a number divided by something that's going to infinity, a constant on top, divided by something going to infinity is going to give me 0, which is what I wanted to show. So then, since this is the case, we could say, Well then, the sum that we have, which is the sum from n equals 1 to infinity, this was negative 1 to the power of n minus 1 times 6 over 2n plus 5, is convergent as an alternating series by the alternating series test. And again, I'm abbreviating that AST. Let's go ahead and take a look at another example here. I want to test for convergence or divergence. And so don't be alarmed that this is alternating differently. Here the first term happens to be negative, and then positive, and then negative. So it doesn't really matter. So it can alternate the other way, no problem. I still want to go through the same test. It's still regarded an alternating series, of course. In this case, my b sub n is 8n minus 1 over 9n plus 1. And this isn't so clear. So this is not something that I would say it's at all reasonable to work with inequalities or sort of, small colloquial arguments. The derivative is going to help. So for this, if I'm checking that first condition to see if these terms are decreasing in magnitude, I want to build a function with continuous variable x. I don't want discrete variable n for this process. Derivatives need to be with continuous variables. Just as a reminder, this is on the interval from 1 to infinity. We'd say, well, let's go ahead and differentiate this. So here, f prime of x, I'll use quotient rule, no reason not to. Bring the denominator up to the top. Derivative of the numerator is 8. Minus, rewrite the old numerator. Derivative of the denominator is 9. This is all over the original denominator squared. And then I want to clean this up as best as I can. So if I distribute in, let's say, well, 8 times 9x is going to give me 72x, and then plus 8. Over here, I want to distribute the 9 in, but I also want to bring my subtraction in. So I'll say, well, 9 times 8x is 72x, but I'm subtracting it, so minus 72x. And then a negative 9, but I'm subtracting it, so that's plus 9. And then all over 9x plus 1 quantity squared. And if I'm looking at what's happening here, 72x minus 72x is going to cancel. 8 plus 9 is going to give me 17. So we get f prime of x is 17 over 9x plus 1 squared. Well, hold on a second, though. This is a problem. What this is saying is my derivative is positive. If I plug in any value from 1 to, onward until, I can't really plug infinity in, but if I keep plugging in values away from 1, moving in that, positive direction, as x gets larger, I'm always going to have something positive in the bottom, and I have something positive on top, and the ratio of two positive things is going to be a positive quotient. So I'd say, well, though this is bad, f prime of x is positive, which means that I'm positive that this is increasing. LOL. And that's not what we want. So in fact, what this means for that first condition is that b sub n plus 1, I wanted it to be less than or equal to b sub n. That's not true. So that's not good. Sad face. Kind of even looks like an angry sad face, because maybe we're feeling that emotion too. Who knows? So this right away, we're noticing there's an issue. If I were to move on to that second condition, we're still going to see some bigger issues. So if I were to say, well, let's say I didn't do this, though we should. If I took a look at the limit as n goes to infinity of 8n minus 1 divided by 9n plus 1, we would use our favorite trick, right? We would say divide through by the highest power of n in the denominator. So we have 8n minus 1 on top, 9n plus 1 on bottom. And we would say, well, let's go ahead and divide everything by n. Let's see what happens here. So if I were to go ahead and reduce now, we'd say, well, this gives me the limit as n goes to infinity of, here we have 8 minus 1 over n divided by 9 plus 1 over n. And as n goes to infinity, 1 over n goes to 0. So I get 8 minus 0 over 9 plus 0 gives me 8 over 9. And this does not equal 0, right? So that second condition of alternating series test is going to fail as well. And that's now a very concerned, sad face. We're seeing exactly how grave the situation is. Very scary stuff. So what are we really trying to say here? Well, we could go ahead and claim that alternating series test is failing, and of course that leads us to see that the series that we have is divergent. Really, when that's the case though, when the alternating series test fails, what we really want to be considering then is test for divergence in some sense. So we're really thinking about this, we're saying, well, since the limit as n goes to infinity of b sub n equals 8 over 9, there's no way that the series can converge. So here we can go ahead and say, well, since the limit as n goes to infinity of b sub n does not equal 0, the series will diverge. Now let's say by test for divergence. And if you really want to think about what's happening as we're going on with the series, now, these terms end up increasing as we go on and on and on, but eventually get close to the value 8/9 in magnitude, and all the while alternating. So at some point in our sum, we're going to be adding 8/9, minus 8/9, plus 8/9, minus 8/9, plus 8/9, minus 8/9, so on and so forth. So we're not going to be able to settle anywhere. The sum isn't going to converge. It's going to sort of end up jumping between these two numbers as we get very far out in it. And that's not going to end up giving us an answer, right? So we'll say, well, in that case, we can sort of see we have this divergence, or the alternating series test failing. Let's take a look at one more example for alternating series test. I want to test the series for convergence or divergence. Here we have the sum from n equals 1 to infinity of negative 1 to the n. And we have n over the square root of n cubed plus 2. And right away we can see that b sub n is this n over square root of n cubed plus 2. And I want to see if this is decreasing or not in magnitude. So let's model it with a function of continuous variable x. So here f of x, you guessed it, is x over square root of x cubed plus 2, which I'm even going to rewrite this just for making the derivative a bit easier, though this is going to be some good practice. I'll say x times, and here we'll do x cubed plus 2 to the power of negative 1/2. And now when I go to find f prime of x, I want to work with product rule and chain rule. So if I rewrite x, we'd say the derivative of stuff to the negative 1/2 gives us negative 1/2 stuff to the negative 3/2. And I can rewrite my inner function back inside. It's x cubed plus 2. And then times the inner derivative, which is 3x squared. And then I can add to this. Now I can rewrite the second term, which is x cubed plus 2 to the power of negative 1/2, and then times the derivative of the first term, but the derivative of x is just 1. So there's my derivative, or the start of it at least. And I want to clean this up. So we'll say, well, let's go ahead and see if we can do a little bit more with this derivative that we have here. I'm going to try to write this as a fraction, this first term. So it's negative. I have an x times 1 on top, so minus x, divided by, in the denominator, I have a 2. Well, I'm sorry. I also have this 3x squared that I was sort of neglecting. So I have a negative x and then a times a 3x squared on top. And then here in the bottom, I can take this x cubed plus 2 to the negative 3/2, and I can bring that down and make it x cubed plus 2 to the positive 3/2 power down there. And then plus, and I'll make this into a fraction as well, and that's going to be 1 over x cubed plus 2 to the 1/2. Now, in order to say something about this, I want to try to get a common denominator, right? I want to try to get some common denominator here. So what I want to do, well, first let me clean up this first fraction, since I sort of forgot this term, but there it is. I have a negative, that's 3x cubed, and then divided by, here I have 2 times x cubed plus 2 to the power of 3/2. And then plus, here I have 1 over x cubed plus 2 to the 1/2 power. But I want to get a common denominator so that I can write this as one fraction. So to do that, I would say, well, now here, to the second fraction, I can build that common denominator by multiplying by 2 times x cubed plus 2 divided by 2 times x cubed plus 2. And this is going to give me this common denominator. My common denominator is going to be 2 and then x cubed plus 2 to the power of 3 halves. And my numerator is negative 3x cubed plus, and if I distribute through, this is going to be plus, forget about the 1, but I have 2x cubed plus 2 times 2 is 4. And then I can just clean this up just a little bit more. And we'll say f prime of x is equal to, in the numerator I have negative x cubed plus 4 divided by 2 times x cubed plus 2 to the power of 3 halves. And I want to know, is this negative? Well, remember, we're considering this on the interval from 1 to infinity. If I look at the denominator first, 2 is positive. If I'm thinking about positive numbers for x and cubing them, they're going to be positive. And then adding 2 is still positive. Raising them to the 3 halves power is positive. So there's no mistake that the denominator is positive, which means the denominator doesn't dictate the sign. If the numerator, whatever sign it has, is going to tell me what this is. So since the denominator is already positive, if the numerator is positive, the whole situation is positive. If the numerator is negative, the whole thing is negative. So I just really need to focus on the numerator. I'll say, well, when is this negative? When is negative x cubed plus 4 less than 0? When is it negative? If I add x cubed over to the other side, say, well, then 4 must be less than x cubed. And this isn't always true, right? And if I'm thinking about this interval from 1 to infinity, and remember, this is a continuous variable, but at some point we want to return back to a discrete variable n, where n stops at 1, and then 2, and then 3, and then 4. We'll say, well, so this doesn't happen at 1, right? 1 cubed is not larger than 4, but 2 is. 2 cubed is bigger than 4, right? We'll say 8 is bigger than 4. So this isn't perfect, but we talked about this back with the integral test. We say this is eventually decreasing. And then it's going to be decreasing from there on out, which is fine enough. And if I'm really upset about that very first term of my series not being part of that decreasing behavior, I can just pull that one to the side and add it in manually and say, well, let me look at the rest then. And if the rest is convergent, adding one more finite term won't disrupt that convergence. So that's sort of the idea, is we really take a look at the infinite part of the series, and if there's some small amount of finite terms, or it could even be many finite terms as long as it's finite, then it's not going to disrupt the results, right? I only care about the infinite part of the infinite series, not any finitely many terms that are sort of messing with what I'm trying to rock and roll with. So this is eventually decreasing. If I return back to that discrete variable n, we would say, well, it's not decreasing at n equals 1, but for n equals 2, 3, 4, so on and so forth, it is decreasing. And that's good enough for what we're trying to do. So we're going to get a pass for that first condition, say b sub n plus 1 is less than or equal to b sub n. It does have that eventually decreasing behavior, which then now I want to look at my limit. And so I want to look at the limit as n goes to infinity. It was n over square root of n cubed plus 2. Now here I want to divide by the highest power of n in the denominator. The power of n in the denominator is kind of tricky to see because it's not an n cubed, it's a square root of n cubed, or that's n to the 3 halves power. But I still want to employ that trick. I would encourage you to work with a root then. Instead of writing it as n to the 3 halves power, I would say, okay, let me give a little fraction bar here. Think about dividing everything by the square root of n cubed. So divide the bottom by square root of n cubed, divide the top by square root of n cubed, and then go from there. Now in the numerator, it certainly is safe to rewrite this as some fractional exponent that might even be preferable. Say n over n to the 3 halves for just this step, and we'll clean it up next. Divided by, here in the bottom, what I can do is I can actually use the quotient property of the radical and say, well, this is going to be the square root of, and now I can do n cubed over n cubed, writing it all as one radical, and then plus 2 over n cubed. And this is just the property that we have, I'll jot it down up here, where we would say that the square root of b over a is the same as square root of b over square root of a. Or a over b would probably sound a little bit better, but I already wrote it. Well, no, I don't want anybody to make fun of me on the internet. Why did you do b and then a? I'll say, I don't know. But I fixed it. Same property, right? Didn't really lose or gain anything. But this is what we're talking about. I can use this property, and then from there, I did split up the fraction underneath. So at first I was thinking square root of n cubed plus 2 in parentheses all over n cubed. Then I broke up the fraction. I did that in one step to save on some precious space here. Now, I can go from here, so let's keep working with this. Say we have the limit as n goes to infinity of, I say n over n to the 3 halves. If I want, though, I could say n to the 3 halves is n times n to the 1 half, and then divided by square root of, here I have 1 plus 2 over n cubed. So we get limit as n goes to infinity of 1 over, I could say square root of n for n to the 1 half, divided by square root of 1 plus 2 over n cubed. And now I can talk about what happens as n goes to infinity. Well, 1 divided by square root of n, as n goes to infinity, square root of n goes to infinity, so I get 1 divided by something headed to infinity, which gives me 0, divided by square root of 1 plus 2 over n cubed goes to 0, which does give me 0. So this one was a bit more sort of involved, a bit more work, but here we have the series, and here we have the sum from n equals 1 to infinity. What was it? And this was negative 1 to the n, n over square root of n cubed plus 2 is convergent by the alternating series test. So we do get that convergence. Let's talk about now 11.6. Let's talk about absolute convergence along with the ratio and the root test. And this is some of my favorite material. So here we have some definitions that we're going to go over very quickly. Remember, should have already watched the lecture material for this, but here we're going to sort of talk about it a bit more. We have a series, the sum of a sub n, is called absolutely convergent if the series of absolute values, the sum of the absolute values of a sub n, is convergent. And at first, if we're thinking about how it sounds to our ears, it kind of sounds like we're just really sure that it's convergent. We say, oh, is it convergent? Oh, it's absolutely convergent. But that's not what that means. That means convergent when we throw the terms in absolute value. So now we're sort of considering if anything has a minus sign attached to it, we're stripping that minus sign away. We're looking at the magnitude of each of the terms, each of the addends, and we're adding up anyways. And if it's still convergent, then we have a very strong convergence known as absolute convergence. There is another type of convergence, we just didn't have a need to discuss it before now, known as conditional convergence, and that's a weaker convergence. And here we say a series, the sum of a sub n, is called conditionally convergent if the series that we were given is convergent, but not absolutely convergent, meaning the series we have is a convergent series, but as soon as I put the terms in the absolute value, it's no longer convergent. We lose that convergence when we look at absolute convergence, which is a weaker convergence. We say conditional convergence. And when talking about absolute convergence in general, we say if a series is absolutely convergent, then it is convergent. So we have sort of this, we should really be specifying on conditional convergence. It's helpful to say absolute convergence. So this is more sort of letting us know that if you say it's convergent, you're kind of implying that it is absolutely convergent. So if it's not absolutely convergent, you should be specifying that it's conditionally convergent. But I think it's just great to use either of these terms, just to be clear. The ratio test, which we're going to start with, says if the limit is, if we look at first, the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So we're looking at a ratio on our generating term. And let's call that limit capital L. If this happens to be less than 1, then the series is absolutely convergent and therefore convergent. But if that limit gives us something that's greater than 1 or something that's infinite, then we say the series is divergent. One sort of sad thing about the ratio test and the root test as well we're going to see is that if the limit gives us 1 right on the nose, then the ratio test is actually inconclusive, which means we don't know if it's convergent, we don't know if it's divergent, we have to do another test. So if this happens, this third part, which we don't like, this means we have to try another test. So there's got to be something else to do. In the root test, we'll talk about that when we see an example. We'll end with an example of the root test today, but it has very similar consequences. We're just now talking about working with, roots instead. So let's take a look at the ratio test here. Determine whether the series is absolutely convergent, conditionally convergent, or divergent. Now, what I'm looking at here is the sum from n equals 1 to infinity of n divided by 5 to the n. And what we're staring at is what we consider to be a sub n. So here I'm going to say a sub n is n over 5 to the n. But I'm also going to want to look at a sub n plus 1. Now, to find a sub n plus 1, all I want to do is substitute any mention of n with n plus 1. So the n on top became n plus 1, 5 to the n became 5 to the n plus 1, and now I want to look at that limit. So it was the limit as n goes to infinity of the absolute value of, and getting that ratio correct, we want a sub n plus 1 on top and a sub n on bottom. And so here, absolute value of a sub n plus 1 over a sub n. So now I can just actually compute this limit. We'll say limit as n goes to infinity, absolute value of a sub n plus 1 is n plus 1 over 5 to the n plus 1. And that's all divided by a sub n is n over 5 to the n. And we wouldn't want to keep it as a fraction divided by a fraction. And this happens, I think, pretty often with the ratio test. So we're going to want to write this as multiplication by the reciprocal, right? So I'm going to keep the numerator the same, n plus 1 over 5 to the n plus 1. But then I'm going to multiply by, and I'm going to flip the bottom fraction. So 5 to the n on top divided by n, still in the absolute value for everything. And I want to work through this limit. So what I can do to start is I can actually break up this 5 to the n plus 1, sort of breaking away a power there. We'll say limit as n goes to infinity. I have n plus 1 divided by 5 to the n plus 1 I can write as 5 to the n times 5. And then I'm just going to leave this other piece the same, 5 to the n over n. But now some stuff is going to cancel, right? 5 to the n on top and bottom cancels. And I'm left with the limit as n goes to infinity of the absolute value of, I have 1/5, which I'm just going to bring out in front a bit, but still inside the absolute value. I can actually bring it outside of the absolute value since it's positive, times, here I have n plus 1 over n. That's what I'm going to focus on the most. And here I can actually just work with this algebraically by splitting up the fraction. So we'll say, yeah, let's do this. Limit as n goes to infinity. Absolute value of, we got 1/5 times, we have n over n, which is going to give me 1, plus 1 over n when I split that fraction. And now we can take a look at this limit, right? We'd say 1 over n is going to go to 0 as n goes to infinity. So I get absolute value of 1/5 times 1 plus 0, which is going to give me absolute value of 1/5, which it's positive, so bring it out. It's just regular 1/5. And this is what we get. This is our limit. We call this capital L. But we want to think about what the consequences of ratio tests say. I got this limit capital L 1/5. Since it's less than 1, 1/5 is smaller than 1, the series is absolutely convergent. So we'll say since L equals 1/5 is less than 1, our series, which was the sum from n equals 1 to infinity of, what was that, n over 5 to the n, n over 5 to the n, is absolutely convergent. And therefore convergent by the ratio test. Always want to mention the test that I'm using. So we have a convergent series by ratio test. Let's take a look at this example here. So here we want to determine if the series is absolutely convergent, conditionally convergent, or divergent. And right away looking at this, I'd say, well, this maybe isn't something that we would want to use ratio test on right away. In fact, what I would do if I saw this, and this is sort of a good, it's frustrating, but it's a good sort of time for us to talk. Let's have a little bit of a conversation, you and I. We'd say, looking at this, if I didn't know that I was supposed to be talking about ratio test right now to each and every one of you on the internet, I would say, looking at this, it's an alternating series, definitely, and it looks like a great candidate for the alternating series test. So I would start this with sort of going rogue a bit. I would say, let me take a look at the alternating series test. My b sub n, if I strip away this alternating sign, is 1 over 5n plus 1. If I model this by a continuous variable, so I say look at f of x, which would be 1 over 5x plus 1, or I could say 5x plus 1 to the power of minus 1, then my derivative would be negative 1, 5x plus 1 to the power of minus 2 times 5 by chain rule. That's what we're doing here. And if I clean this up, we'd say, well, that's negative 5 divided by 5x plus 1 squared. And that the derivative is negative. So there's my workup there, but I could say f prime of x is negative, which means that f of x is decreasing. So that first condition, b sub n plus 1, is less than or equal to b sub n. Check. The second thing I want to check with my alternating series test is the limit as n goes to infinity of b sub n. The limit as n goes to infinity of 1 over 5n plus 1. And here as n gets larger, 5n plus 1 grows without bound. 1 divided by that gives me 0. So this is a convergent series right away. So I can actually mention, well, this is convergent by the alternating series test. But now we have that follow-up question, is it absolutely convergent? So if I take a look at this in absolute value, the sum from n equals 0 to infinity, we'll say the absolute value of, here we have a negative 1 to the n over 5n plus 1. So if I throw that absolute value, well, now the alternating sign is no longer alternating. And we have the sum from n equals 0 to infinity of, now we just have 1 over 5n plus 1. Now what I would do, and this is, I don't want to get too crazy with something that's going to happen in just a bit, is I would actually take a look at breaking off the very first term. When n is 0, I just get 1 over 0 plus 1. So I might want to write this as 1 plus the sum from n equals 1 to infinity of 1 over 5n plus 1. There's a reason why I'm doing this, and you'll see why next. But I'm going to want to test this series. I think the best way to test this series is with the limit comparison test. We talked about that a bit ago in a previous video. But so what I have here to start with a sub n is 1 over 5n plus 1. And I'm going to compare this using a limit with b sub n, which is just going to be 1 over 5n. And remember, for the limit comparison test, so I'm using LCT now, limit comparison test, I want to look at the limit as n goes to infinity of the ratio of these. So 1 over 5n plus 1 divided by 1 over 5n. I don't want to divide a fraction by a fraction, so we'll say limit as n goes to infinity of 1 over 5n plus 1 times 5n over 1. And then we'll, write this as one fraction. We have 5n on top divided by 5n plus 1 on bottom. And here we'd want to use our favorite trick, divide by the highest power of n in the denominator. So we'll divide everything by n. And this is going to give me the limit as n goes to infinity of 5 over 5 plus 1 over n. And as n goes to infinity, 1 over n goes to 0. And this gives me 5 over 5 plus 0 gives me 1. Now, I'm not using ratio test, so I don't have to worry about that sort of third case of ratio test. I'm using limit comparison test. And if you remember from what we said back in 11.4, we call this value capital C for Corey. And since this value is positive and finite, this means both series behave the same way. This means both series behave the same. So I was looking at comparing against the sum from n equals 1 to infinity of 1 over 5n. And this is, if I want to write it, 1/5 the sum from n equals 1 to infinity of 1 over n, which is divergent. So we'd say this is divergent. This is the harmonic series, or it's a failed P series. I'm not trying to make anyone feel bad. No, I won't make any P series feel like they're not good enough, but it's not gonna pass as a P series. It's the harmonic series if I want to reference that too, which means that the sum that I had, which I kind of adjusted it to be the sum from n equals 1 to infinity of that was 1 over 5n plus 1, is also divergent. There's a few things I want to mention before I write out this final result for this one. I did something kind of messed up here, right? I brought out this first term when n equals 0, which was just 1. The reason why I did that was if I kept this sum at n equals 0 for starting, I couldn't really talk about the series that I'm comparing against starting at n equals 0. Because when n is 0, 1 over 5n is undefined. So that's a bit of a problem. Does it really affect the result? I mean, not really, but you have to be willing to ignore that discontinuity, which isn't a good thing. We want to be sort of thinking about things as mathematically as possible when we're doing mathematics. So I went ahead and I actually adjusted this earlier on to say, well, let me bring out the n equals 0 term. And this is just a finite addend. So this isn't going to tell me if it's divergent or convergent. I want to look at the infinite part of it. And now I can talk about starting at n equals 1. And I can compare this with limit comparison test and get a nice clean result that has no division by 0, that's not going to upset anyone or anything like that. I also want to mention that if you were to try the direct comparison test with these, you wouldn't be successful. It wouldn't work out the way we need the inequality to work out, which is kind of unfortunate because it is a bit of a quicker test. But this tells me all that I need to know. So what did we find out from all of this? Because we did actually a lot of work for one problem. Alternating series test. It was convergent. My series is convergent. But when I threw that same series in absolute value to try to check for absolute convergence, it failed. Which means it's convergent but not convergent enough. It's convergent but not absolutely convergent. So what I had to start, which is the sum from n equals 0 to infinity of negative 1 to the n, all divided by 5n plus 1, is conditionally convergent. And there's actually a nice sort of side conversation here that we're not going to really have time to talk about, but it's worth sort of exploring. This is mimicking the alternating harmonic series. So I'll say it as I'm boxing this. The harmonic series diverges, but the alternating harmonic series as an alternating series is convergent. And if you really want to sort of, ruin your day, either your week or your weekend, take a look at the sum from n equals 1 to infinity of negative 1 to the n over n, the alternating harmonic series, and use the alternating series test. You're going to see that this actually converges. And that's frustrating because the alternating series for the harmonic series is a conditional convergence, which is very interesting. Harmonic series diverges, but the alternating harmonic series converges. So that's really cool. Cool stuff to think about. Let's take a look at another one. We're going to get back on track with ratio test, I promise. Here we have the sum from n equals 1 to infinity of n factorial over 3 to the n. What I'm staring at in all of its glory, my generating term, is a sub n. And if I want a sub n plus 1, I just have to swap out any mention of n with n plus 1, so that's n plus 1 factorial over 3 to the power of n plus 1. And now I want to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And that's the limit as n goes to infinity, absolute value of, on top I have n plus 1 factorial over 3 to the n plus 1, and then divided by a sub n is n factorial over 3 to the n. And again, I don't want to divide a fraction by a fraction. I'm not trying to do that here. So I'm going to fix it, multiply by the reciprocal instead. I'm going to leave the numerator the same, n plus 1 factorial over 3 to the n plus 1, and then times. I'll flip this, 3 to the n over n factorial. Let's say limit as n goes to infinity, absolute value of. Now I can start breaking things up. Let me start in the denominator. 3 to the power of n plus 1, that's 3 times 3 to the n. And I can just write sort of selectively that other numerator. I'm also going to leave n factorial alone, but thinking about factorials, I can write n plus 1 factorial as n plus 1 times the remaining n factorial. So inside of any larger factorial is a smaller factorial, and I can take this and sort of use it to my advantage, because now I could say, well, 3 to the n on top and bottom cancels, and n factorial on top and bottom cancels. So I'm left with, from my work, I'm left with the limit as n goes to infinity of the absolute value of, almost everything's gone, I'm left with n plus 1 divided by 3. And we'll say, well, as n goes to infinity, the numerator goes to infinity, and then dividing by 3 doesn't do anything, right? So this is going to give me something that's infinite. And this, so this is what we're referring to L, right? Since our limit was, infinite, this means that our series diverges. So we can go back to what we said about it all the way back. So here our limit gave us infinity, means our series is divergent by ratio test. Let's skip back through. It was from n equals 1 to infinity, n factorial over 3 to the n. So the sum from n equals 1 to infinity of n factorial over 3 to the n is divergent by the ratio test. We'll take a look at one more example, and this is going to be an example of the root test for us. So let's see what the root test has. Now let me just go back. We'll talk about what root test is all about, but it has the same consequences as ratio test. So it's not going to be brand new, but it is a different test. They're very closely related though. So we talk about them at the same time. So if we have the limit as n goes to infinity of the nth root of the absolute value of a sub n, we take a look at that limit, it gives us something out, we call that something L. Depending on what L is, we know what we're working with. And it's the same consequence, right? So I just have to remember, okay, now I'm taking the nth root of the absolute value of a sub n. If L is less than 1, we have absolute convergence, therefore convergence. If L is greater than 1, or if it's infinite, divergent. If L is equal to 1, the root test is inconclusive. So let's take a look at this. Let's take a look at an example of the root test and see what that's all about. So what I'm staring at, my generating term is a sub n. That's n squared plus 8, all divided by 9n squared plus 3, and that's all to the power of n. And I want to look at the limit as n goes to infinity of the nth root of the absolute value of a sub n. So I want to take a sub n and throw that inside my absolute value. So that's my n squared plus 8 divided by 9n squared plus 3, all to the power of n. And what I can do from here is I can actually make a comment. N is going from 1 on to infinity and just stopping at those integers along the way. So n equals 1, then n equals 2, then n equals 3, then n equals 4, then n equals 5, so and so on and so forth. all of these exponents then are positive, right? If they're 1 or 2 or 3 or 4, they're positive exponents. So I can actually bring this absolute value bracket inside and just focus it on the base. So we'll say the limit as n goes to infinity of the nth root of, and now I'm going to have the absolute value of n squared plus 8 over 9n squared plus 3, and then that's in the absolute value, but then to the power of n. And what's going to happen now with root test, almost like too perfect of a situation, is the nth root of stuff to the n, those are going to cancel. So this just leaves me with the limit as n goes to infinity of the absolute value of n squared plus 8 over 9n squared plus 3. And you know what we're going to do here inside that absolute value. We're going to use our favorite algebraic trick for limits, for rational functions like this. Lily's going to help out, of course. We're going to divide everything by n squared. And we're going to reduce. See what we get. So we got the limit as n goes to infinity. Absolute value of, here I have 1 plus 8 over n squared, all divided by 9 plus 3 over n squared. And I can take a look at what happens as n goes to infinity. As you say, as n goes to infinity, 8 over n squared goes to 0, 3 over n squared goes to 0. So I get absolute value of 1 plus 0 over 9 plus 0. That's the absolute value of 1/9, which is going to give me 1/9. And this is our value, capital L. So I'd say capital L is 1/9, which is less than 1, smaller than 1, which means we have that absolute convergence. So I'd say, so the sum from n equals 1 to infinity of, and this was n squared plus 8 over 9n squared plus 3, all to the power of n, is absolutely convergent. And that's by the root test. That's what we looked at here. So we have absolute convergence with the root test. Hey, thank you so much for spending your time with me, taking a look at some of these interesting problems. Make sure you're keeping up with the homework and everything like that. If you have any questions for me, you know where to find me. You know where to find Lily. We're here to help you. So let me know. Let me know how you're doing with this. And otherwise, no matter what, remember to always keep learning, keep dreaming, follow your heart. And I will see you next time. And until then, make sure you take care. Bye.